Okay, so let's look at a pretty simple, well, kind of simple gravity example problem. I don't know if I mentioned it already, but gravity problems are not simple. I apologize for saying that. So here's the problem that we're going to look at, and it's going to give us really a good workout in lots of different things involving the force of gravity and gravitational fields. We have this probe that we're sending down towards the surface of a planet, and it's starting 3 radiuses or radii away from the surface, which means really it's 4 radii from the center. But as it goes down there, it's measuring the strength of the gravitational field. And I even fitted it with this magical drill that lets it drill down to the center of the planet without having any problems, but continuing to take measurements of the gravitational field strength as it descends. So our mission is to draw the graph that will represent how the strength of the field is going to decrease over time, or not decrease, but change as it approaches. So to go through this, let's start by drawing a free body diagram, which is what we should do for every problem involving forces. So the only force acting on it is the force of gravity. So we can just say that this thing's going to have an acceleration equal to the force of gravity, that's the sum of the forces, over the object's mass. And I'm just going to write P right there as in the mass of the probe. So then I can extend that out and say this is G, mass of the, we'll call it, oh, I shouldn't have used P, mass of, let's call it planet X. So I'll just do mass of planet X times the mass of the probe all over the distance between them. And since that distance is changing, I'm not going to put any numbers in there. I'm just going to put in R to hold my place. And that is all divided by the mass of the probe. So you can see force of gravity is right there, mass of the probe is there, but now I have mass of the probe in the numerator, mass of the probe in the denominator, they can actually cancel. And as is going to happen so many times, mass just doesn't matter, usually if we're talking about the object itself. The mass of the planet's mattering, but not the mass of the object itself. So this just simplified down to G mass of X all over R. Oops, that should be squared again. That's the second time I've done that tonight. There we go. We have acceleration equals G mass of the planet all over R squared. Um, Now what we want to do is just recognize that this acceleration right here is the acceleration due to gravity, because gravity is the only thing that's affecting this probe as it goes down. And that means it's the same thing as the strength of the gravitational field. The acceleration due to only gravity, or the free fall acceleration, is equal to the strength of the gravitational field. So if you can find one, you can find the other, like we just did. So what I'm going to do now is I'm just going to plug in some different versions. We'll do it for what it's like at 4 radii away from the center. That's right now, that's highest point. Then we'll do it at 3 radii. That would be about here. Then we'll do it at 2 radii. That would be above the planet's surface, but not in the planet's on the planet yet. We'll do it 1 radii. That's on the surface of the planet. And then finally, we'll do it at 0 radii. That's the center of the planet. So if I plug that in, that would be G times mx over r squared. Well, the G and mx, we don't have values for it, but they don't really change. But over 4r, that's going to be 16r squared. Okay, so there's our first value. Our next value, let's do it in a different color, that way it doesn't get too crowded. This is the 3r. That's going to end up being gmx over 9r squared. My next one, the 2r, is going to be gmx over 4r squared. And then my next one, my r, is going to be gmx over r squared, because now it's just 1r. And then finally, if I divide by 0, we're going to have a problem here. Oops, I should do this in red, because I can't actually divide by 0. But there's more problems than just that in doing this calculation. So I'm going to save this one for now, and I'm just going to start transferring these over. Here's the assumption I'm going to make. I'm going to make it the assumption that just like on Earth, let's just call this one G. So my point at 0r, right there at the surface, oops, I should make it orange so my points match. We're going to call that just G. Whatever the value of G is on this planet, that's G. You can see that this is 1/4 of G. It's the exact same other variables, but it's 1/4. So that puts me right there. You can see that I kind of did some prep before I started this. This is 1/9 g. Everything's the same except there's a 9 in the denominator. So that gets me down to 1/9. And then finally, we have 1/16, which is there-ish. And you can see the shape that it's making here. This is a very characteristic parabolic curve. And it makes sense that it's a parabolic curve because we have the r squared in the denominator. That means that it's an inverse relationship and it's an exaggerated inverse because it's squared. So that's where that's coming from. But then from here to like the center of the Earth, that's where the real question comes up, and that's where students tend to stumble a little bit. The temptation is to say, oh, well, at the center of the planet, uh, R must be 0, so there must be infinite force of gravity. But if you think about that, you guys know that that's not true. If I asked you just a question of, okay, I hollow out the center of the Earth, I stick you in there, how much gravity do you feel? What direction are you being pulled in? You guys would get it right away. You'd be like, oh, I wouldn't feel force of gravity at all. And if I asked you why, you'd say, well, oh, because I'm being pulled in all directions because the mass is all around me. It's not underneath you anymore. It's everywhere around you. So actually, the strength of the gravitational field inside the Earth or inside this planet would actually be 0 because you are like inside of it. And as you've gotten deeper and deeper into the planet, when you're like here, instead of having all of the mass pulling you down, you have some mass pulling you down and some mass pulling you up. So as you descend in there, it gets weaker and weaker. So I'm actually not going to prove the rest of this, although if you want to come to office hours and ask about it, I'd be happy to. But it ends up just being a straight line as it gets through there. It has to do with the way that as you're going deeper and deeper, the mass is decreasing by by a cubed rate, roughly. So I can explain that to you. It has some interesting things with calculus in there and stuff, but it's not really that important. The important thing is to recognize that we should have a curve out here, and it should definitely be 0 right at the center of the Earth. This part is more interesting, but not essential knowledge for you guys at your level. So there's that example problem. Make sure that you understand the concepts in here because this had a lot of like really good physics meat to it. And other than that, just have a great day. Thanks for watching.